Hey, Barb, you should be a panelist and a co-host now that you can unmute. We could just make sure everything is okay.
Can you hear me?
Yep, we can hear you.
Oh,
Cool.
great. Awesome.
We'll start in about 2 minutes. I have this up right now. The way it'll work is I'll introduce, I'll give just some of the rules with the webinar, and then you'll present for the whole time. And then at the end of it, we'll take questions from people in either the chat or interactively. So it goes smoothly.
Great. I already told Jim that I have 70 slides, so we'll see.
Well, we have all.
I'm a fast talker. I can get through it. It'll be great.
All right, we'll get started. So for everyone here, thank you for joining our Continuing Near LEHIGH seminar series. Today we're starting with Dr. Barbara Simpson, and I'll give you an introduction to her. Dr. Simpson, she's an assistant professor at Oregon State University. She received her PhD from UC Berkeley and her Bachelor of Science from the University of Kansas. She uses advanced computational experimental methods to characterize structural response. Her aim is to develop innovative structural systems that improve building performance and reduce the effects of natural hazards on the built environment. Research areas include resilient design and retrofit of building structures, performance-based earthquake engineering, and next-generation computational modeling and simulation, such as the development of hybrid simulation methods for wave structure interaction. And before we begin, I just want to make a note that during our presentation today, we will ask that if anyone has any questions or comments or wants to make a note, please use the chat or the Q&A that's available to you. We will not be unmuting anybody during the presentation. We'll take all questions at the end. And if we do want to have an open discussion, we'll open up anyone's channel to do that. So without any further ado, Dr. Simpson, I will ask for you to present. You should be able to share your screen and then start your presentation.
Okay, let's try this. How about this?
All looks good on my end.
Awesome. So thanks so much for the introduction. So I'm going to be talking about a system that's rather near and dear to my heart. I've been working on it for quite some time. So today we're going to chat about higher mode force demands in systems employing elastic strongback spines. And what you'll find is that I tend to default to calling these systems with a strongback, but they're known by a number of different names depending on who you talk to. So there's a lot of other researchers that are also looking into this topic. But just to give a walkthrough, oh my, it is not moving. Okay, I guess I have to click. To give a roadmap of what this presentation is going to go over, so we're going to introduce this problem of story mechanism behavior. That we're going to introduce it in terms of brace frame systems, but of course this is an issue that you see in a number of other systems as well, as we'll see throughout this presentation. And then we'll look at a possible solution, which is where this Strongback concept comes in. And here I'm going to sort of switch between calling it a Strongback and calling it a spine, depending on which project I'm sort of introducing. Like I said, there's a lot of different research that sort of has been looking into this topic. And then we'll go into sort of characterizing the nonlinear and dynamic response of these systems, particularly in terms of higher mode effects. And we'll talk about some ongoing research and applications of the system outside of how it was originally developed. And so let's look at this first part, this problem of story mechanism behavior. So this is a building, observed damage after the 1994 Northridge earthquake, a very conventional brace frame system. And all these dots represent some sort of inelastic response, in this case, brace buckling mostly, as well as some connection failures. And what you see is that almost all of these dots are concentrated in the second story. And this is pretty indicative of what we're going to call a story mechanism behavior, where you're utilizing the energy dissipation capacity of one story, but you're not leveraging the energy dissipation that's in all these other stories of this 4-story building. And so this was the premise, not only the only reason for this research project, but this was a research developed during the Nice days. So when I originally started my PhD working with brace frames, it was still Nice rather than Neri. And this was a collaborative research project looking into these sort of vintage brace frames and their vulnerabilities. And from this project, I became sort of interested in story mechanism response and how to mitigate this story mechanism response. And so throughout this project, we tested a number of brace frame specimens that are typical of sort of vintage brace frame construction. So those brace frames built or designed prior to the 1988 Uniform Building Code. And this was the first test that we did, a 2-story conventional brace frame test. And we saw a number of different damage states, a number of different types of deficiencies. But something that I want to point out is that when we did this test, we saw most of the damage was concentrated in the first story. Again, fairly indicative of a first story mechanism. And in fact, we did 2 sort of vintage brace frame testing. And if the first specimen formed sort of a weak second story, then the second specimen we tested, which was almost identical to the first test, except we filled all the braces with concrete. We got this sort of a weak beam mechanism where, again, almost all the damage was concentrated in the first story. And so this was sort of the story mechanism behavior that was really the precursor to a lot of the work that I'm going to present today. And so if we sort of look at, if we take a step forward from vintage brace frame construction into sort of modern US provisions for the seismic design of let's say, brace frames, we've done a lot. So there's decreased section stoutness ratios to delay or even prevent severe local buckling and fracture. We've introduced buckling restrained braces, which have more stable energy dissipation capacity compared to braces that buckle. We've improved the detailing of our gusset plates to allow braces to buckle out of plane. We've also developed a number of simplified capacity design procedures to have more realistic estimate of member forces due to brace buckling and yielding. And yet there's still this issue that brace frames, as well as other modern systems, despite the fact that we've had these number of different improvements, they still tend to form story mechanisms where the damage is concentrated in one or a few stories. And so that's where this possible solution comes in, this idea of this elastic Strongback spine, which was really, I would say, the brainchild of my advisor, Dr. Stephen Mahan, who actually passed away during the course of this research when I was doing my PhD. But he, as well as others, had sort of recognized that there was a number of different ways we could mitigate this story mechanism behavior and mobilize the full energy dissipation capacity of the entire system. And so if you look in the literature, there's a number of different ways that people have approached this problem. There's dual systems where you can use a sort of secondary system to apply some elastic restoring and capabilities. There's the continuous column concept, where if you have a continuous column spanning over the height of a building, either some sort of gravity system or something different, then you could span over the story mechanism problem. You could think of steel plate or concrete shear walls as a stiff, elastic vertical element that imposes a more uniform drift distribution, thereby delaying these storing mechanisms, rocking and self-centering systems. And the one on the right, you're seeing sort of a precursor to what I've been calling the Strongback brace frame, but sort of a zipper frame, which leverages an idea of a weak beam and sort of a vertical tie strut. So as the braces yield and buckle, it sort of pulls down on this vertical tie to engage adjacent stories. And so that was sort of different ways that people have approached, or researchers have approached, this storing mechanism problem. And it's useful when introducing the Strongback system to sort of think about it in terms of why storing mechanisms form. So let's take a brace frame, and let's say that each brace in every story has an equal strength or compression capacity C and an equal stiffness. So these are the same braces used throughout the story, and it's subjected to some sort of seismic or inertial loading, let's say in this case an inverted triangular distribution. And so when the braces in the story buckles, then you're going to get a loss of both strength and stiffness in that story. And unless there's an appropriate mechanism to distribute these demands, in this case from the columns, those demands are going to tend to concentrate in a single story and potentially lead to a story mechanism behavior. And so that's kind of the reason why these storing mechanisms are so prevalent in these brace frame structures. And so this concept of a conventional brace frame has this tendency to form a storing mechanism due to this brace buckling behavior. Then the Strongback system is sort of this concept of let's introduce an essentially elastic mechanism that provides an elastic load path to distribute demands. And so this gray sort of box area here is a portion of the brace frame system that we're going to design to remain essentially elastic. And then it's going to be able to distribute the demands across multiple stories. So instead of, on this figure on the left, 100% of the damage concentrated in one story, we're going to utilize this sort of elastic mechanism to distribute the demand across all 4 stories. So now you're getting a quarter of the damage distributed across this 4-story building. And so that's sort of the concept of the Strongback brace frame. And then outside of that elastic Strongback, you're going to sort of design and detail the elements to yield and dissipate the seismic input energy. So in this case, how the Strongback brace frame has been traditionally formulated is that you have these primary fuses, which could either be yielding or brace buckling behavior that dissipate that are the primary energy dissipation mechanism. And then you also could have secondary fuses, for example, flexural yielding and sort of these longer beam lengths that provide some secondary energy dissipation. And so going back to this original sort of research into these vintage brace frames, we had this first test that formed a second story mechanism, the second test that formed a first story mechanism, and then the idea of this third test as part of this research was to introduce this Strongback concept to distribute the demands over both stories. And so this gray triangle here is what we're sort of envisioning as the Strongback retrofit scheme. And how the Strongback works, if we were to look at it in terms of its kinematics, this gray box, that's the Strongback, is designed to remain elastic. And initially it was formulated as this sort of pivoting type motion, where this gray box sort of pivots back and forth. And then you have some sort of primary energy dissipation. In this case of this experiment, we were using buckling restraint, a single buckling restraint brace. And then because that pivoting motion induces a vertical deflection in the beam, you could also say that there's a secondary sort of fuse in terms of flexural yielding in this beam length. And so we built and tested this at full scale. And this figure on the right is just sort of that pivoting motion. And you can say, that you can see that that we were successful in distributing the demands across both stories and achieving a more uniform drift distribution. So in that respect, this experiment was rather successful, and here we're seeing this sort of Strongback, this elastic portion of this frame. And this was a result of a number of different collaborations. The vintage brace frame experiments were part of a much larger collaborative research program between Berkeley and the University of Washington. I happen to be the PhD student at Berkeley, and then Andrew Sen was another PhD student at University of Washington. And then from this, there became interest in how do we look at this system in terms of design development. So AISC also became interested in this project, and that sort of leads into the second portion of the research, which, how do you characterize these force demands in the Strongback spine? And the reality is that the previous experimental test, although valuable in sort of introducing the concept and showing that it was successful in distributing story drifts, demands more uniformly with the building, it didn't actually look at the dynamic response. It was tested in a quasi-static way, no inertial effects, etc. And so prior to this sort of portion of the research, there've been a number of numerical studies looking at this. I've only listed a few. There's many more beyond these three that I've listed here. And there were some experimental tests that had been conducted. There was some hybrid simulations that have been conducted on a similar system. And then there was the experimental test that I just introduced on this two-story Strongback system. And actually at the same time, they were building and constructing very similar systems. This one's called the Masted Frame. You can see that it looks very similar to many of the images I've shown so far by tipping structures in Berkeley, California. And so we were having this sort of numerical analyses, experimental testing, and then sort of it was being constructed at the same time, but there were still these really large questions on how these systems behaved, not only in the inelastic range, but in terms of their dynamics. And it turns out that when you look at the response of these systems, they behave quite a bit differently compared to sort of traditional conventional systems that are designed to be ductile and exhibit inelastic behavior in every mode. And so this was a major question for us. And I like to describe this in these sort of figures. So I actually didn't develop these figures. These are from a seismic design course that was taught at UC Berkeley by Steve Mahan. And I've sort of leveraged some of these images in presenting this idea, but this is not a new concept of looking at force demands in the elastic components or the force controlled actions of a system. And so here, for example, we have a moment resisting frame where the plastic mechanism is typically flexural yielding at the ends of the beams, as well as potentially at the column bases. And here we have this moment frame subjected to an inverted triangular distribution. And if we're interested in the moments in the columns, well, we know the flexural strength of these beams, and so we can get the column moments. However, during an earthquake, if those applied forces change, then what you see is that the moments in the columns also will change. And as the inertial forces change again, you'll see that those column moments also change again. And so the elastic regions really may not be that well constrained by flexural yielding or the formation of these plastic hinges. And what you could potentially do is run a number of different nonlinear dynamic analyses for a number of different ground motions, collect them statistically, get their median values, and then design for something, some sort of statistic level of confidence for the moment in the columns to design them to remain elastic. And so that's sort of the example of a force demands in sort of a conventional system that we very much know. The same sort of idea can be extended to this Strongback system. So if you take this Strongback system, you can apply some sort of assumed inertial force distribution. That's going to result in some sort of story shear demand. And then if we just sort of, I'll move this to the left. If we just sort of do a section cut through this Strongback brace frame, what you'll see is that the forces, let's say in this Strongback brace, which is denoted by this PSJ, the Strongback brace force is going to be some sort of combination of whatever the inertial forces are applying in terms of story shear and whatever forces in the opposite. I call these typically nonlinear braces. So the brace that's considered to be yielding in this case. And so what you can say is that force in the Strongback brace is coming from a combination of sort of story shears that are developing during the ground shaking from the inertial forces, as well as whatever axial force demand is being developed in the opposite brace. And sort of keeping that in the back of your mind, what you can see is that as that applied force distribution changes, the story shears will consequently also change. And even if that brace force is at its expected yield strength, if it's a BRB, the forces in the Strongback brace in this case will also change. And if those forces change again, those story shears would change again, and the forces in the Strongback brace change again. And what you end up seeing is that the force demands that are most significant or could be most significant in the Strongback portion of this system, are actually ones that correspond to a force distribution where there's a reversal in the force. Here, there's a reversal of the force at the top story, which is, or top floor level, which is typical of, say, a second mode distribution. And so what you tend to see is that the higher modes actually play a very dominant role in the forces in the Strongback. And so if you look at nonlinear dynamic analyses, so this is that same 4-story building subjected to a suite of nonlinear dynamic analyses, and this red line here, solid red line, is sort of the median from those ground motions, median force level in the Strongback braces, and then the Strongback tie is just this vertical element that you see here. And then also the 85th percentile is shown. If you were to just look at a first mode distribution, and let's see if I can make this a little bit smaller. If you were to just look at the first mode distribution, like so an inverted triangular force distribution, and you were to do a plastic analysis and get the forces in the Strongback, what you would get is this solid black line here, which is lower than the 15th percentile of what you're going to extract from nonlinear dynamic analyses. And that's because of these second mode force demands, which play a very significant role in the forces that tend to accumulate in these elastic regions in the Strongback itself. Now, there's a number of different ways we can explain this. I prefer to sort of take this approach from the concrete shear wall. So if we take a concrete shear wall that has some sort of first mode-like inertial force distribution, and we were to have it form a plastic hinge about the base of the wall, and then the remainder of the wall were to remain elastic. So the moments at the base of the wall are constrained by the strength of that flexural hinging at the base of this wall, and the base shear would then be whatever that moment at the base of the wall is divided by the height from the base to that force resultant. Now, what you happen to see is that if that inertial force distribution changes, let's say due to contributions from the second or higher modes, then that force resultant will shift downward because the higher modes tend to, or the second mode in particular, tends to be associated with the force reversal. And now, even if that moment at the base of the wall remains the same, because we're still getting flexural hinging at the base of the wall, you're gonna also see that h hat, in this case, that height to that force resultant becomes smaller, which means that the base shear can become smaller. And so even though the moments in this system at the base of this wall are well constrained by flexural yielding, the base shear in this case, and even the story shears, are not so well constrained. And even if you look at the moments above the base, they're also not so well constrained. And so that's sort of the same principle of what's happening in the Strongback system. In the first mode, you're getting sort of limited forces due to the yielding mechanism. So I introduced them previously as primary yielding and say the braces, or secondary yielding in the beams. Those are limiting the forces in the first mode. However, that nonlinear mechanism is not necessarily limiting the forces in the second and higher modes. And so what you can see is, as you make this Strongback more and more stiff, you're going to get this sort of averaging of drift demands with story height. And so that tendency for a story mechanism to form, or for the system to concentrate damage and demands in a single story, will be reduced, and you'll sort of get this more uniform drift distribution. But what you'll also get is increasing story shear and acceleration demands due to the presence of these higher modes. And those are arising because the Strongback is designed to remain elastic in every mode, which is different than conventional systems where we expect inelastic response in all modes. And so you can see here, as that Strongback becomes more and more stiff, the story shear demands will also increase. Now, what becomes really interesting is when you look at different ground motion inputs. So here we have a number of different response spectra for different ground motions, in this case 4. And what you'll see is that the story shear demand, and thus the acceleration demand in the system, will heavily depend on the type of ground motion input. So we can see this solid gray line here and this solid gray line here. They have fairly small pseudo accelerations or spectral accelerations at the higher mode periods of the Strongback system. And so you're not seeing as much of this higher mode story shear response. However, if your ground motion happens to have very large spectral accelerations or intensities at the higher mode periods, then what you're going to see is those are going to sort of be in the elastic range and also contribute more to the story shear and acceleration response. And so there's a dependency of the force demands that are highly related to what kind of the characteristics of the ground motion that you're actually applying and how it sort of interacts with those higher modes. Now, here's another sort of example of a BRBF system, buckling restraint brace system, where the inertial forces are sort of decomposed into the first mode, second mode, third mode, fourth mode, and then the total response. And this is just to compare what you might get with the conventional system compared to what's happening in these Strongback sort of elastic spine systems. And what you'll see is that the BRBs yield, and you're getting a primarily first mode response, and then the forces in the second and higher mode are still limited by sort of the ability of this system to be able to form storing mechanisms in the second and higher mode. And so you're not getting sort of large higher mode response in the system. It's primarily operating in that first mode response. What you end up seeing with the Strongback system in this figure on the bottom is that the BRBs, or these nonlinear braces, those primary energy spacers, will tend to yield in what looks like under a first mode force distribution. But if you look at the Strongback is really activated, and that's kind of shown by these colors, really when under that second mode distribution, when that second mode force distribution becomes dominant. So if we replay this again here, what you're seeing now is you're seeing that Strongback sort of light up, the force demands in that Strongback spine sort of light up, really when you're getting very, very large second mode force contributions. And this is just summarizing that. So in the Strongback system, we're seeing that the BRBs are primarily engaged under that first mode type force distribution, but you're getting very significant, the Strongback, because it's elastic, is picking up very, very large second mode force distributions that the Strongback needs to be designed for in order to remain elastic in that second mode. So the inelastic portions of the system are really being subjected to that sort of first mode pivoting response. But what you're also seeing is that the Strongback needs to be designed for everything else. So to impose this first mode pivoting like response, it needs to be designed for everything else other than that pivoting first mode, which means it needs to be designed to remain elastic under the second and higher modes. And so there's a number of different ways we can sort of approach this problem. So this is sort of an idea of how do you design the Strongback to have enough strength and stiffness. And one way to incorporate these higher mode effects is, of course, through nonlinear dynamic analysis. And so you could say, I'm going to run a number of different ground motion records, and they're all going to result in different force demands on the Strongback spine. I can then say that due to record variability, I'll take, say, the median plus 1 standard deviation or some statistical confidence of that demand, and I'll compare it to some sort of capacity in the Strongback elements, accounting for material variability, construction quality, etc. And that's going to allow us to sort of say, well, we want to make sure that that demand is less than that capacity, including variability in the ground motion record and the associated force demands, as well as whatever capacity we're getting in the Strongback braces. And then you could say, we're just going to minimize the probability of having any inelastic response at some hazard level. And so that's one way to approach this problem. Now, the issue with this is that a lot of the intuition can be sort of lost in summary statistics, as well as this is not necessarily a practice that would be relevant to every design office. And so there's been a lot of work sort of looking at how do you approach this in terms of static analysis, so you don't have to do an entire nonlinear dynamic analysis. And so here's an example of a not so rigorous modal pushover analysis approach that sort of describes the difference between this BRBF behavior and the Strongback behavior to gain some sort of intuition of the response. And so you can imagine a typical BRBF. If you do a pushover analysis in the first mode, then all the BRBs are going to yield. And if you can see with this base shear versus roof drift ratio plot on the right here, the forces after the BRBs yielded are limited. And if you were to take that same BRBF and subject it to sort of second mode response with a force reversal at the roof, what you would see again is that the resistance of this system is primarily dependent on the BRBs, and so those BRBs will again yield, and you'll see that the base shear versus roof drift ratio response, that base shear force is again limited in the second mode. So this is that sort of typical BRBF behavior. And if you were to look at sort of the modal base shear in the first and second mode, if that system were to remain elastic, what you would see is that the strength in both the first and the second mode of a traditional BRBF system is significantly less than that sort of elastic level base shear. And so you can say for this typical BRBF system, you have this sort of limited strength or very small higher mode contributions in the second and the higher modes. But what you'll see with the Strongback system is that you'll see that same sort of response in the first mode. So that's sort of like this pivoting like first mode behavior. So you subject the Strongback to this first mode pivoting type response. And you'll see that with the BRBs yielding and the secondary flexural yielding in the beams, you're still going to get a base shear response that's below that elastic base shear level. So the forces in that first mode are still limited by your whatever your nonlinear mechanism is. In the second mode, things get a little bit more interesting. So you can still get yielding in the BRBs in this case, but because of the presence of the Strongback, which again, the Strongback is designed to remain elastic, you actually have very significant strength in what I'm going to call higher mode bending. And if you look at, say, the base shear from the ground motion, if you were to take that ground motion, say, look at an elastic response spectrum and say, this is the base shear required for the system to remain elastic, that's this horizontal blue line here, you would see that this system actually has significantly more strength than that blue line. So you need to design that Strongback to remain elastic above the elastic base shear level associated with the whatever hazard you're looking at. And so because you can still get some inelastic response, in this case in the BRBs, I've been calling these near elastic higher mode effects. And to remain elastic in all modes, or for the Strongback in general to remain elastic, that's sort of the purpose, the design strategy of the Strongback system, it needs to be designed for those force levels. And so one of the procedures that has been proposed is you can sort of think about this first mode response as a sort of a plastic mechanism response, something that's yielded in the first mode where the forces are limited. And so you can form a pushover analysis or a plastic analysis in that first mode. And then you can sort of think about the second mode as this sort of near elastic or partial mechanism response. So there's going to be additional force demands that are sort of picked up through this higher mode bending. And then you can think of other mode shapes, in this case it's a 4-story building, so 4 translational modes, for example, as being near elastic but very small modal contributions. So here's the third mode and then the fourth mode, and then you can sort of use modal pushover analysis to then combine the response from each of these modes using some sort of modal combination rule. In this case I'm just showing SRSS, or sort of a superposition rule where the higher mode contributions are then superimposed upon this sort of inelastic first mode. And I just like to point out that there is a paper on this that it has been accepted, but there's a number of theoretical inconsistencies with this sort of analysis approach. For example, you're sort of combining modal responses in the nonlinear range, which we know that is not theoretically consistent. But what you'll end up seeing is that sort of thinking about this sort of inelastic first mode with a partial mechanism response in the second or even the third mode, and then elastic response in the higher modes, actually gets you fairly close to what you end up seeing from the nonlinear dynamic analyses, despite its theoretical inconsistencies. Another way of sort of looking at this problem is through a modified response spectrum analysis. So there's a number of different researchers that have proposed methods for looking at other types of similar elastic systems like concrete shear walls or rocking brace frames in terms of a modal response spectrum analysis. And you can say that, say, the first mode, while you're achieving some sort of inelastic response and you're limiting forces in the first mode, so maybe you can use an R=8 for BRBF system in the first mode, but then in the second and higher mode, you are seeing these sort of near elastic higher mode force demands, and so you could use potentially an R=1 in the higher modes, and there's been a number of different analysis strategies where you modify the structural model to then do these analyses in the second and higher modes. And I've just listed the work down below. And so that sort of brings me to this third part. So I've introduced this idea of these near elastic higher mode demands that are significantly different than what we think of when we think of these conventional seismic force resisting systems that yield in every mode or form a mechanism in every mode or can just form a storing mechanism. What you see in the Strongback system is these very large higher mode demands that can be associated with sort of an elastic response. And so when we start looking at applications and implementations, we really, instead of describing the Strongback as inducing a pivoting type response with a more uniform drift distribution, I started thinking about the Strongback as more compensating for anything other than this pivoting first mode response. And so you can think of this Strongback more as a spine then that propagates demands through bending in the higher modes and thereby providing some sort of increased design flexibility. And so rather than thinking of the Strongback as just this singular brace frame system, there was an effort to start extending it to other types of systems. So for example, in a concrete shear wall, you can have a wall that's pinned at its base that is really responding in much the same way with much the same design premise as a Strongback system. You can think of an uplifting rocking brace frame, which again has this very stiff elastic component, but that uplifts about its base. And so the overturning moment is controlled by this rocking mechanism, much like this pin base is in the wall on the left, which is all related to sort of this pivoting Strongback brace frame that you see on the right, where we have this sort of gray box representing the Strongback, the elastic portion of the system, that then pivots back and forth about the pinned base. And so you can start saying that these near elastic higher mode demands are actually very similar across all of these systems, and that each of these actually belong to a family of, say, elastic spines. And there's a number of different examples of spine inspiration in practice. This is actually just a photo that I took on my very ancient iPhone when I was in Japan a few years ago, where you could sort of take an elastic exterior spinal system and think about it in terms of a tall building. I already mentioned the sort of mast or Strongback concept that was implemented by Tipping in Berkeley. And then there's also the Tesla Gigafactory done by Greg Luth and Associates in Exponent in Reno, Nevada. And something that I like to point out with this last one is that they sort of all have this ability to constrain moment about the base. And so that you're talking about a stiff elastic system that then is pinned about the base of the Strongback or spine. And so it's not intended to provide supplemental lateral strength. It's more to engage the building more uniformly over the full building height. And there's been a number of sort of these idea of pinned base spines here, for example, as a concrete shear wall. And we can see this sort of connection at the base, this sort of very nice concrete machined pin. And then you can have some sort of shear yielding elements and then provide the energy dissipation. So these are all sort of in the family of these elastic spine systems. And so that's where this new project comes in, and this is a collaborative project called the Frame Spine System with Force Limiting Connections. That's a collaborative project between LEHIGH. I'm now at Oregon State University, and then the lead PI, Larry Fanasek, is at University of Illinois. And then there's a number of Japanese collaborators that are also collaborating on this project. And so we can sort of extend that idea of Strongback system, which was initially developed for brace frames, into the concept of delaying or preventing storing mechanism response in a moment frame. And the same concepts still apply. You still need a mechanism to distribute demands. And often we think about that in terms of the strong column, weak beam design requirement to sort of limit concentrated demands in one or a single story. And so you can imagine taking that moment resisting frame, we can now introduce sort of an elastic vertical element to distribute those demands, which again is this sort of spine concept, that it's pinned at its base. It provides an elastic load path to distribute demands uniformly, and then is also designed to remain essentially elastic. And so you have this spine that can distribute demands more uniformly with building height, but then you also still have this higher mode effects that tend to come into play. And I'm just going to show the same slide that I showed previously. And so you have the effects of the higher modes that are not well constrained by the nonlinear mechanism. So even though you have yielding, in this case, in the base MRF due to flexural yielding at the end of the beam, you still have these higher mode effects that are not well constrained by that base MRF yield mechanism, that side sway mechanism. And so to mitigate these sort of higher mode demands, a lot of work was done at LEHIGH to sort of develop a force limiting connection. And a force limiting connection is a yielded connection that's sort of sandwiched between, in this case, the base moment resisting frame, but it's really any conventional system, and then an elastic Strongback spine. And so you use this yielding component that limits the transfer of force demands from the elastic spine to the base system, in this case of an MRF. And because it limits that transfer of forces, it can then reduce the acceleration and the force demands that we're seeing from these very significant higher mode effects, these near elastic higher mode effects. And so this is an example of a potential force limiting connection between the spine and the base MRF. In this case, it's this U damper developed by Nippon Steel, one of our Japanese collaborators. And you can see that it's this green line here between the spine column and the base MRF. And then there was a number of other force limiting connections that were also developed by LEHIGH. In this case, we can see a tongue FLC, which again is this sort of yielding mechanism between the spine and the MRF that's designed to reduce these acceleration and force demands. And so now we can say, well, we can have a spine that's designed to remain elastic, to induce more uniform drifts, but we can also sort of control our accelerations by having a yielding component between that spine, that Strongback system, and the base frame. And so as part of this study, we sought to sort of test this hybrid spine force limiting connection, or FLC, idea. And so we actually were able to leverage an existing shake table study being conducted by the Japanese at the E-Defense shake table. And so the original study was testing a 4-story moment resisting frame that was connected through this walkway to a 3-story base isolated building. And both structures had non-structural hospital equipment that were acceleration sensitive. So then we could look at the sort of impact of having the higher mode accelerations. And so what we did in the study is we made use of this existing 3-story base isolated building, and we locked the isolators, and then we retrofitted it with our spine force limiting connection idea. And so if this was the original 3-story building with base isolators, we added a 4th-story to better look at these higher mode effects. We also added stiffening beams that allowed us to connect the spine to the MRF and sort of distribute those demands a little bit better. And then we also pinned the column bases in the base MRF to really induce a severe story mechanism, because again, we wanted to really look at a system with large higher mode effects and then a severe story mechanism tendency. And the higher mode effects are due to the inclusion of sort of an elastic, in this case, column. So the Strongback spine that was connected at all 4 floor levels to the base MRF. So that's going to induce the higher mode force demands. And then we're also going to add a sort of second case where we have these force limiting connections between the spine and the base MRF. And again, we use those U-bar FLCs and those developed by Nippon, and those tongue FLCs that were developed at LEHIGH. And so between these 2 specimens, this sort of spine plus base MRF, where those FLCs were locked and not engaged. And so you can sort of think of that as a very stiff connection between the spine and the base moment resisting frame. And then the FLC active case, where we had these deformable yielding connections to mitigate higher mode acceleration demands between the spine and the base MRF. And this was the sort of from concept to actual testing. And so this was an experiment that we completed in December of last year. And you can see the spine the stiff, strong, elastic, Strongback spine with the potential FLC locations and the additional force story. And in preparation for this testing, we looked at a number of different ground motions. So this is a suite of 80 plus ground motions for sort of a 10% probability of exceedance in 50-year hazard level for sort of a site in Oakland, California that was consistent with the original moment resisting frame. And what we can see is these blue lines. The dotted line is considering composite action in the beam, and the solid line is just non-composite action in the beam. So there's not much difference there. That blue line is for the bare moment resisting frame, no spine, and then this red line here is for the Strongback system. So the moment resisting frame with this elastic spine column. And each of those 80 plus records were organized from largest to smallest peak story drift ratio. And what you can see is from this blue line is that base MRF, where we've pinned the column bases, has a very strong tendency to form a severe first story mechanism. And in fact, many of these ground motions caused collapse. And you can see from this y-axis, you're looking at very, very large peak story drift demands that are indicative of collapse. The numerical model really, that's kind of outside the range of the numerical model for some of these ground motions. But what you're also seeing is that depending on the ground motion record, you're seeing these increased higher mode acceleration demands. So those are ground motion inputs that have large contributions near the higher modes, large spectral intensities near the higher mode periods. So it's not consistent for every ground motion case, but for many of the ground motions, you're seeing very large higher mode contributions depending on those sort of spectral characteristics. And so we selected a ground motion to sort of achieve not huge story drifts. We wanted to be safe during the shake table testing. So some sort of story drift ratio less than 3%. And then we were also very interested in sort of accelerations associated with non-structural damage, because these structures originally had this hospital equipment. And so we wanted to induce rather large higher mode acceleration demands that were around 2G. And so we ended up selecting this ground motion 48 here, which corresponded to a Northridge ground motion record that gave us reasonable drifts. So we were pretty safe, but also so we could observe these very large higher mode contributions that are coming from the fact that we've implemented this spine. So notice that this blue line is associated with the base MRF, which has a severe story mechanism tendency, and that story mechanism is limiting the acceleration response. But when you add the spine, you can really pick up those higher mode accelerations that you're seeing in these red plots on this bottom plot here. And so we selected that first ground motion to sort of look at these higher mode response. So that blue line here is corresponding to that previous ground motion selected on the previous slide, which had really significant spectral accelerations at the second mode period. And then we also selected the JMA Kobe record to then look at it had tended to have large spectral displacements near the first mode. And so that allowed us to look at sort of different ground motion characteristics, because that particular ground motion record didn't have as large contributions near the second mode period. And so this is just an example of the pre-test numerical simulations of the MRF by itself, the MRF with the addition of the Strongback column, and then the MRF with the Strongback and these force limiting connections. And what you'll see is that with the MRF alone, you get a really severe first story mechanism tendency. So that's this figure on the left. And like I said, this is pretty much beyond the range of the numerical model at this point, but associated with collapse in the structural model. With the spine, you get a much more uniform of drift, drift distribution across the building height. So the peak drift demands are decreased, but you're also seeing damage occurring in every story. And you're seeing something similar. So still sort of this uniform drift distribution, slightly larger peak drift demands, but you're also seeing yielding at these FLC locations, which then are allowing us to sort of mitigate some of the higher mode acceleration effects that can affect those very sensitive non-structural components. And so when we look at the peak story drift ratio for the Northridge and JMA Kobe earthquake, and we compare sort of the peak response for each of these scale factors, so that those ground motions were scaled from 10% to 100%. So this black line here shows the MRF. this dotted line shows the MRF with the spine system, and then this other dashed line shows the contribution from the FLCs. When we look at this numerically, what we see is that severe first story mechanism in the MRF by itself. But when we add the spine, even with the FLCs, although the FLCs do result in somewhat larger drifts, but not the large drifts that we saw for the MRF alone by itself, you see a really vast reduction in that peak story drift demand. And that's because of the presence of the spine, which distributes demands more uniformly. When we add the FLCs in, so that's that force limiting connection between the spine and the base MRF, what you see is that the higher mode accelerations are reduced, and compared to the spine just by itself. But that's highly dependent on which ground motion we're looking at. So for the Northridge ground motion record, there's a definite decrease in that higher mode accelerations. That Northridge record has a lot of content, spectral content at that second mode period, but you're not seeing something like that in the JMA Kobe record, and that's because it tends to have much smaller content near that second mode, or smaller intensities near that second mode period. So that dependency, that decrease in accelerations really does depend on the ground motion input. And so this is just the test last December. So this is 100% Northridge. The FLCs are not active in this case, and you can see the non-structural components. And so we got fairly large acceleration demands with the spine directly connected to the MRF, so without that yielding force limiting connection. And you can see here that there was some toppling of some of the equipment, which could be really disastrous for some of these hospital buildings. So acceleration hospital equipment shown here. And so this is still an ongoing study funded by the National Science Foundation. It's very collaborative between the US institutions as well as the Japanese researchers. And I just really want to say a heartfelt thank you to all the graduate students in this project who were really instrumental in moving this project forward. So that's sort of an example of one application. Another one that we've sort of been working on is extending the spine concept or the Strongback concept from steel and sort of concrete shear walls to also mass timber. And the nice thing about mass timber is because it's a relatively new material, has a number of sustainability benefits, it's really uniquely positioned to foster innovation. And so what we're seeing in the mass timber world is that there's a lot of push to go towards more performance-based design concepts, next generation enhanced performance systems. And so these ideas of spines, of an elastic component to distribute drift demands more uniformly with building height have sort of caught on in this world. And so this is just example of another story mechanism. So it's not, I know I introduced this starting out with steel systems, but of course, this is a problem that we can see in a number of other types of lateral force resisting systems, regardless of material. And of course, this is a maybe a little bit dramatic, but you know, these soft story problems are not just problematic in steel brace frames. We can also see their influence in, say, mass timber systems or wood systems. And so you can imagine a mass timber spine. Here we have on the left sort of a self-centering, either a cross-limited timber or MPP rocking wall. So something that uplifts about its base, where the remainder of that spine is designed to remain elastic. And then you can have some sort of supplemental energy dissipation provided by BODs or some sort of steel energy dissipator. Or you can have sort of what we've been talking a lot during this presentation, sort of a pivoting a CLT or MPP spine that's pinned at its base, that sort of pivots back and forth about a pinned base connection. And then you can imagine some other steel energy dissipators in this system as well. And so this conceptually is very similar to what we've previously introduced in terms of that Strongback column coupled with a moment resisting frame, or the Strongback braced frame where you have a Strongback truss coupled with a conventional brace frame. And so this is something that's sort of a signature test that we're looking at here at Oregon State. And so we have a brand new Red Emerson Advanced Wood Products Laboratory. And in that lab, we're planning on testing this 3-story mass timber system with sort of a spine that's able to swap out from the gravity framing. So we can see it as it sort of like a test bed in this case, where we will then test a number of different hybrid mass timber spines with steel energy dissipators. And so those tests are forthcoming. And again, we have a number of graduate researchers on this project, and as well as a postdoc that have been really fantastic, and a number of partnerships and linkages with ongoing work with the National Science Foundation, as well as from the Tallwood Design Institute. And so in summary, the addition of these elastic spines, which are stiff vertical elements designed to remain elastic, they really can mitigate storage mechanisms and result in a more uniform drift distribution. You also get to utilize the energy dissipation capacity at every story, at every floor level. But they also result in these near elastic higher mode force and acceleration demands. And if you're going to design the Strongback to remain elastic in every mode, you need to consider these very large force demands that will accumulate in the Strongback spine. And they're highly dependent on the ground motion input. You can introduce this sort of force limiting connection idea to mitigate these higher mode demands. So you have some sort of controlled yielding mechanism that limits transfer of the forces between your elastic spine and whatever base frame you're connecting it to. And so provided you tune those FLCs appropriately, you could decrease these higher mode accelerations and still control drift response. And then finally, I just want to say that these elastic Strongback spines do provide this added flexibility. And so because it's an elastic lateral force path, you can sort of think of them as being able to bridge across irregularities. So if you, as an engineer, want to remove any of the nonlinear elements or bridge across mass or stiffness irregularities, then the Strongback allows you to do so. You can also imagine coupling sort of this Strongback system or this elastic spine system with some sort of recentering capability. And then you can also think of it, as has been shown here, in a number of different retrofit cases where this elastic spine or Strongback is then added to an existing deficient structure to then span over some sort of stiffness or story mechanism tendency. And with that, I will open the floor to any questions. And then there's a number of researchers that have been working on this. And so the references were provided on a number of the different slides. But I would be happy to take any questions as needed.
Thanks, Dr. Simpson. Yeah, there's nothing right now. We'll give the attendees a few minutes to compose their thoughts, any questions, and we'll see what we get from there.
Great. I'm opening up the chat.
Liang asks, does a Strongback spine system need to be installed for the entire structure?
No, actually there was it was another nice project, and I'm trying to remember, it was called a stiff core wall or something similar, where they didn't actually extend the, it was a retrofit situation, but it wasn't extended over the entire building height. And you can do it, but it just depends on what that base structure looks like. So if it's a retrofit situation and you have a severe first story mechanism tendency, you can imagine adding the Strongback, let's say it's a 6-story building. You can imagine adding the Strongback maybe across the first 3 or 4 stories. So now you can distribute demands across those 3 or 4 stories, but now you could potentially get a story mechanism right above that Strongback, or right above that 4-story where that Strongback system ends. And so it just needs to be detailed appropriately to make sure you don't cause a story mechanism elsewhere. So that can happen. But no, it doesn't. I've often thought about it as spanning the entire building height, but that's doesn't necessarily need to be every case. It just depends what that base frame is like.
Sorry, I had myself muted. There was another question in the chat from Benjamin Turan. The linked column frame system is a form of spine. Is that correct?
The linked column frame system. I'm not sure what is meant by linked column frame system. Is that the MRF plus spine column that I was showing previously? Maybe I could get.
I give Benjamin a chance to.
Now there has been like sort of these a number of Canadian researchers have been studying sort of like segmented spines, which is a little bit different than this force limiting connection idea that's been shown here. And I shouldn't say it's just Canadian researchers. There's also been some research conducted at Stanford as well, and I'm sure at other places. But basically what it is you have sort of segmented spines where it doesn't extend over the entire building height, but there's some sort of inelastic or nonlinear or some sort of controlled component between the segments. And you can imagine that instead of, if you have one spine, it sort of pivots back and forth. I can't believe I'm doing this with my fingers. But if you have a segmented spine, you can sort of develop this sort of controlled display shape that's not that full first mode pivoting type response. And so you can mitigate higher mode effects that way as well. And so I'm not sure if that's the reference for the linked column frame system.
Well, sorry, go ahead.
Yeah. In my mind, the spine is really a very stiff element designed to remain elastic at some hazard level. And because it's elastic, it can induce these higher mode force demands. And then you're going to have to think of some mitigation strategy if those acceleration and force demands are too large or too significant. You have to think of some sort of mitigation strategy, either through segmented spines, force limiting connections, or some other mechanism of reducing those higher mode effects.
So if he wants to, there we go.
Okay, the linked column is a moment frame with very short distance between the columns, and then the fuse are intermediate beams. That system is being used in New Zealand, and I think some of the research is from Oregon, and it's been from some studies, but it's similar in concept in terms of having a very stiff element and then less stiffer elements attached. So maybe have some relationship, but not sure about it. But sometimes we're not able to put braces, or are difficulties in architectural combine these bracing systems, and I see some similarities between the spine and the linked column system.
Yeah. I'm not sure I'm very familiar with the system you're talking. I'm aware of like the sort of beam column sort of self-centering connection. I don't know if that's kind of similar to what you're referring to. But yeah, if you have this stiff component, I mean, to be honest, you can think of a column as a spine. This is just a mega column. And in fact, when I initially showed this, oh, now my keyboard's not working, but that initially showed that moment resisting frame with the columns, you still pick up those higher modes. They're just not as large or as significant because it's not this huge stiff thing where it's all concentrated in one place. So it's really any vertical component in your system that's designed to remain elastic. But then you can sort of imagine, you can get kind of crazy with the amount of ways you can then control the energy dissipation. And so then it's like, I mean, the field's wide open on how you want to couple that elastic, very stiff elastic system to any other sort of base frame or energy dissipation mechanism. So yeah, it potentially it could have some relation.
Yes, the researcher name is Peter Dushika from Portland State University.
Hmm.
Okay.
Okay. Yeah, thanks. I'll have to look into that.
I guess in the Q&A, there seems to be, I guess, a follow-up when you were discussing the Strongback systems, the construction and testing under real time or real earthquake demands. So I think you kind of alluded to that you were looking into inertial effects of systems under real world examples. Can you elaborate any further on that?
Yeah, let me pull up the Q&A. So there are a number of, and I think there's an increasing number of examples of these sort of stiff elastic components that are actually constructed. But of course, we haven't had an earthquake in the US in quite some time. And so initially, when I had originally looked at this research, it was part of the sort of vintage braced frame study. And so it was like a kind of one-off where we had this test set up and we wanted to look at the Strongback system, but it was under quasi-static loads, and we really hadn't recognized the influence of these dynamic effects at that time. And so we were imposing just an inverted first mode triangular distribution, and it behaved exactly as we thought it was in terms of, sort of this pivoting response that you see in these images here. But then when we started looking at the numerical analyses with dynamic loads and the inelastic behavior, we noticed that there was something really wrong with our initial assumptions. The force demands were huge and the accelerations were huge. And it took quite some time to sort of figure out whether it was the model or whether there was something else happening. And there was something else happening, which was this near elastic sort of higher mode accumulated demands that tend to sort of occur in these elastic elements. And then if you go back and look at the literature, there's literature from the late 70s or even earlier that sort of documents these higher mode force demands in similar systems to the Strongback. So there was the tied eccentrically braced frame. They see the same thing in rocking or uplifting brace frames. The new version of ACI now incorporates this higher mode effects in the design of special concrete shear walls. And so it became quite obvious that this is what was going on based on the relevant literature. The issue was it has shown up in experimental tests, but it hadn't been it hadn't really been studied in terms of like a pinned sort of pivoting spine way. So there's been some shake table testing on rocking systems. There's been a lot of shake table tests where this behavior is observed with concrete shear walls. And so when we looked at the shake table study, we looked at it as an opportunity to not only look at the spine's ability to distribute demands more uniformly, but also the FLC's ability to sort of cap these inertial force demands. And so that, I don't know if you would consider that real, but it was full scale. It was a shake table setting. Granted, we did have to do a number of modifications sort of to induce higher mode demands because the original 3-story building was designed much too well and was too short to sort of see some of these higher mode effects. So we added that 4th story. And then to really see the acceleration demands, you have to compare it to a base system that forms a story mechanism. You can't really see the increase in these higher mode accelerations unless you have a severe story mechanism tendency or even just moderate story mechanism tendency in the base MRF system. And so there were some modifications that make the building we tested a little bit unrealistic, but it still shows the influence of these higher mode effects. And it also shows this really this unique, not unique, it is very good at spanning over irregularities. So despite the fact we had an MRF with pinned column bases with a severe 1st story mechanism tendency, as soon as you added that spine column, the drifts became reasonable, and we no longer we're dealing with these really unsafe collapse potentials. So from that respect, it very successful. And then the FLCs can then be used to look at some of the acceleration factors that start coming into play when you have these spines. it's a very long-winded answer. I don't know if it answers your question, but feel free to keep asking if I'm not quite on the same page.
Well, we kind of expired our hour. The questions were great. Appreciate that, and your time as well. You did blast through those 70 slides very effectively. There is
effective or fast is
sure, we'll leave that up. We'll take this last question, and this will be it. If you're okay with that, if you Q&A, I'll read it out loud. How feasible is the Strongback system for high-rise structures over 20-story in the high seismic region? And what would be the response modification factor for such systems like an R = 8?
Yeah, and it's an open question. So I have looked at for up to 8 stories. I've looked at up to 8-story buildings, and it's pretty feasible up to 8 stories to induce a pivoting mode. So first mode. Beyond 8 stories, you probably want to think about whether you really want to induce a full pivoting first mode mechanism across something like 20 stories. And other researchers have looked into that topic. Takeuchi and Chen at Tokyo Tech, they looked at, I believe there's an earthquake spectra paper where they look at something around 20 stories. A lot of work on sort of like tied eccentrically brace frame systems has been conducted up in Canada, rocking brace frames, etc. I've only gone up to 8 stories because then you're kind of getting to the range that your Strongback is just, it needs to be really stiff. And a brace frame in that case might not give you enough stiffness. You might want to start looking into something more like a concrete wall that's pinned at its base, or a steel plate shear wall that's pinned at its base. And then it becomes a real question of what you do with the response modification factor. So in a lot of my work, I've envisioned it as a modification of a conventional system. So it's a buckling restrained brace system with this additional elastic Strongback component, in which case the BRBF R = 8 makes sense with this, it's still a BRBF with now this elastic Strongback. But really more work needs to be done to better look at what R values you need, what overstrength values you need, what CD values you need in terms of a FEMA P695 type study. And that work just hasn't really, it's been started, but I would say the question's still out there. Another long-winded answer.
And we'll leave that open-ended for another time. So that our next seminar, you could come back and answer that question.
Great, fabulous.
All right, well, we'll conclude with that. There aren't any further questions, plus we've expired. Dr. Simpson, I appreciate your time. We all appreciate your time presenting. And if anybody does have any comments or questions, they can contact you. It looks like you put up your WordPress site here. Is that a good site for people to contact you other than email?
Yeah, I mean, also feel free to contact me through email. The only reason I have this is because a lot of the literature is located on the site. So I'm not the only one working on this, but if you go to any of my papers, there's a very long list of references that'll lead you to some of this other work. So. And
typically with our seminar series, this is recorded, and with permission, we will upload this on the Design Safe website if you're okay with that. So if anybody ever wants to go back and view these. And so that'll be up there. The slides won't be available, but the presentation will. So with that, I'd like to conclude and thank everybody for joining our seminar series. We have another announcement coming up very soon, so keep your eyes open for an email from Design Safe for a next seminar series. And with that, thank you, and this concludes our webinar.